Hey everybody, Mr. Johnston here again. In this part of the video we are going to talk about how to determine cell potential for a voltaic cell. So just a quick recap from what we talked about before. A galvanic cell consists of a substance being reduced in one cell, and that pulls electrons through a wire from a substance that's being oxidized in another cell. And so another word for galvanic cell is a voltaic cell that we talked about in the previous video. This pull, or this driving force of electrons, is called cell potential. And we can actually calculate cell potential in a galvanic cell if we know the reduction potentials. The unit of electrical potential is called a volt. A volt is just a unit of work that is equal to 1 joule per coulomb of charge being transferred. So thinking about like how much energy or how much electrons are going to be going through that wire. It turns out that there are ways of measuring this cell potential. And almost every chemistry textbook has a list of standard reduction potentials. This is a list from a textbook. Our textbook has this same chart. It's actually in chapter 19. It's table 19.1 in our textbook. But the way that these are set up, each one is a reduction reaction. The things at the top of the list are most likely to be reduced. They are the ones that are gonna produce voltage in the reduction process. The ones at the bottom of the list are most likely to be oxidized, and so they actually have negative reduction potentials. And we'll take a look at how to use these values from this table when we go through an example from our guided reading. So all half reactions are shown as reduction, and they're standardized, so that's why they're called standard reduction potentials at 1 molar, 1 atmosphere, and 25 degrees Celsius. When a half reaction is reversed, then the sign of the potential is also reversed. So if we know that something is actually oxidized, then we just flip that reaction and reverse the sign of the cell potential. In any redox reaction, the number of electrons lost has to equal the number of electrons gained. And so sometimes you have to multiply half reactions in order to balance the electrons, but this does not change the standard cell potential. Here's the other thing, is the direction of spontaneity gives a positive cell potential. So the spontaneous reaction is always going to have a positive cell potential. The way that we calculate the cell potential is you take the potential of the cathode, and that's the redox or the reduction portion, plus the anode, which is the oxidation portion. And again, we'll look at some examples of how to do this in just a couple of minutes. So that equation, E cell, is equal to the reduction potential plus the oxidation potential. So the work done by a galvanic cell, we already mentioned this, but work can be accomplished when electrons are transferred through a wire, and it depends on that push-pull idea behind the electrons. That's the cell potential. This equation is on your AP reference sheet, and this equates Gibbs free energy to that cell potential. And remember, a spontaneous process always has a negative sign for Gibbs free energy. So if you think about this, if you have a positive cell potential, then you're going to have a negative Gibbs free energy. The other terms in this, N is number of electrons, and that's the coefficient from the balanced equation, how many electrons are transferred. And F is something known as Faraday's constant, and that's a constant given on that AP reference sheet. The main thing from this equation is that if cell potential is positive, then it's a spontaneous reaction because that'll make Gibbs free energy negative.